Hey geometry friends, here we are looking at section 7.2, similar polygons. We're looking at a couple of vocabulary words. Well, first of all, a similar polygon, if we keep it in mind, is a polygon where one, let's say, one polygon and another polygon have exactly the same shape, but might have different sizes. So the two polygons that you see right now are similar. And what makes them similar is that all of their corresponding angles are indeed congruent. So this angle is congruent to this angle, this one to this one, and so forth and so on. But the interesting thing is that their sides are not necessarily equivalent, but they are, if you remember from our discussion earlier, proportional. And proportional means that if I know that one side is, let's say, A, this side is B, this side is C, this side is D, let's say E, F, G, and H. I know I didn't do that nice and alphabetically, but what this means is that A is to B as E is to D, as C is to F, and finally as H is to G. So the sides are proportional in terms of their ratio. So if this is 2 and this is 4, this is 3, this would have to be double just because 2 to 4 would be 3 to 6 and so forth and so on. And so in a case like that, so this is the definition of similar polygons. They're polygons where their angles are congruent, two polygons or more where their angles are congruent and their sides are proportional, whereas a scale factor is the ratio of one corresponding side to another corresponding side. So I could say that the scale factor of these two polygons would be A to B, or of course, we can write a ratio as A to B. Similarly, I can use any pair of corresponding sides to determine what the scale factor is. So our textbook has this handy graphic to show us in a little bit more detail what exactly a scale factor is and in terms of the definition of what similar polygons are. What I'd like you to observe here that we didn't talk about is when you name two polygons that are similar, you use this symbol in between. Also, you must make sure and name the polygon in order from congruent angle to congruent angle. So you notice that the vertices are labeled with the same color and they're also equivalent angles. In this diagram here, we are given the fact that we have two similar triangles and they name them for us. It is sometimes helpful to highlight the letters that are in common so you can see that F and J are written first, so you know that those are congruent angles. The next one would be G and K, written as the second of each, and finally the last two being H and L. So that also gives me an idea of what, not even an idea, that lets me know what sides are actually congruent to one another, well, proportional to one another. So as I look at this, the side connecting F and J would be proportional. Let me use a narrower one. The side connecting F and G, rather, is proportional to the side connecting G and K. The side connecting G and H is proportional to the side connecting K and L. And you can see that the last side, HF, is proportional to the side connecting LJ. And so that gives me kind of the order of proportionality, if you will. And so what I'll do now is use that information to answer. Use the similarity statement up here, which is here, to list all the pairs of congruent angles and write the proportional sides. Take note, I would honestly not even need the picture in order to do that. I can look and say, oh, F is congruent to J, G is congruent to K, and H is congruent to L. So with these facts listed, again, I could use my diagram, or I could simply look at the order again to determine which segments are proportional. So FG is proportional to JK, GH is proportional to KL, and then finally I can do something like FH is proportional to JL. And that information can be written like this. Here we're given some pictures. This is the initial picture that we're talking about here. In this particular quadrilateral ABCD or rectangle ABCD, we're given this picture and Kuma is doing some resizing, and we want to know, is A proportional to this original picture? And we would check that out by observing the angles. We can see that these are two rectangles, so all of the angles are 90 degrees, so we've got the equivalent angle piece, but what we need to do is see if the sides are proportional. So I would take 8 to 12, and I'm going to see if that's equal to the same thing as 10 to 14. And I'll put a little question mark here. One way of checking that out is to cross multiply. We remember that the product of the means is equal to the product of the extremes. And so that gives us the right to cross multiply. And if the products that we multiply together don't turn out equal, then we know we don't have a proportion. Or we can reduce them. So I'm going to reduce them because that's easier than multiplying numbers that I don't feel like multiplying right now. So 8 over 12 can be reduced to 2 over 3. And 10 over 14, can be reduced to 5 over 7. Clearly these aren't equivalent, but even if you had a question, we've now reduced it so that the cross products will be easier to deal with. 5 times 3 is 15, and 2 times 7 is 14. Though the numbers are close, they prove that we don't have proportionality. So these two images are not similar. Let's try this one. Again, we're going to set 8 or compare 8 to 12 and see if that's equivalent to 10 to 15. Again, we can reduce, seeing that 8 to 12 can be reduced to 2/3. We do that. Remember, reducing is just dividing the top and bottom by the same number. We see that this can be reduced to 2/3 as well. Clearly they're equivalent. Clearly their cross products would be equivalent. So we know here that we have in B at least a similar polygon to our original. So here in example 3, we've got to be pretty careful about what angles and what sides are congruent to what. So here it might be helpful to highlight or draw a picture just because we're going to be finding information about it, or draw on the picture that you have. So I see that AC is congruent to, or is the corresponding side to VW. So I'm going to highlight that, and that looks pretty obvious. And then CD, let's see, where's CD here? CD corresponds with WY, and that's over here. And then we can take it from here. DF is, no, wrong color. DF there corresponds with YZ. Add a little red in there. And then finally, this last side, which is FA, corresponds with ZW. And so having that lets me know what things I can create my proportions out of. I really do think that that's an important step. All right, so if we need to find X, I definitely want the side with X in it. So I'm going to start with the small one and go to the big one. 10 over X is equal to, so if I start with the smaller figure and go to the other figure, I need to continue that relationship. So now what I'm looking for is two sides that are just given, and that would be this green side and this green side, 6 to 9. So that gives me two numbers that I don't have to have variables to deal with, so I can easily find my X. So now I'm going to do what I do best, which is to cross multiply. 9 times 10 gives me 90. 6 times X gives me 6X. After I do that, dividing both sides by 6, I get 1, remainder 3, and 15. X is equal to 15. Now that I have that, that gives me a little bit more ammo when trying to solve other parts of this picture, of this situation. So here I'm looking for Y. Y is given in this purple side. So I'll do what I did before. I'm going to start with 3y minus 1 over 12. Notice I started with small triangle or figure to larger one. And if you're going to make a proportion, you want to continue that. You want to continue the process of going from one thing to the other thing. So at the top, I'm going to talk about the small figure again, and maybe I'll use 6 with 9, or I could use 10 with 15. Doesn't matter. I'll use 6 with 9 though. Small to large, 6 with 9. Cross multiply just as I did before. This time a little bit more involved. I got to rock the distributive property, but we are friends with the distributive property. 12 times 6 is equal to 9 times the quantity of 3y minus 1. And here's where we're using the distributive property. 12 times 6 is 72. 9 times 3y is going to be 27y. And don't forget 9 times minus 1 gives me a minus 9. Moving the 9 over to the other side, it's going to become a plus 9. I get 81. You guys see that? I'm going to try not to skip too many steps, but I get 81 is equal to 27y. And if you know like I know, you can divide by 27. Don't want my songs? Don't worry about it. Y is equal to 81 divided by 27 is 3. And so y is equal to 3, and we have solved the problem. Which brings us to this awesome theorem, Theorem 7.1, perimeters of similar polygons. Did you know that if two polygons are similar, then their perimeters are proportional to the scale factors between them? Say what? Most definitely. So you remember how we knew this side is to this side, as this side is to this side? Well, guess what? The sum of all of this has the same scale factor as the sum of all of this, meaning I can add up all the sides of one and add up all the sides of the other, and that ratio will be the same as the corresponding sides to each other. All right, much fun. Let's go ahead and see if we can apply it somewhere. So here's example 4. We're going to use a scale factor to find the perimeter. So we see that these two pentagons, 1, 2, 3, 4, 5. These two pentagons are similar. We're going to find the scale factor of each of these and the perimeter of each polygon. So let's see if we can do it. One thing I'm observing here is these hatch marks, which tells me that this side and this side are congruent. So I get to write 8 and 8 here. And these two sides are congruent, which is 4 and 4. Lovely. So that gives me some good information. So I know that this side is 3 and this side must be 3. And so I think that's enough to help me find the whole thing. Let's make sure we're find the scale factor and then find the perimeter. Cool beans, I can do this. The scale factor will be determined by finding the lengths of two corresponding sides, and we've got that. I'm going to do small to large. It doesn't matter. I could do large to small, but let's do small to large just because I'm going to keep that consistent. Sometimes I write a little thing here to let me know what I'm doing in terms of keeping the order of my corresponding sides. So if I'm going from small to large, it's going to be 3 to 4. You guys see that? 3 to 4. So I do 3 to 4. Right? And then I can say, well, I know the perimeter of this guy. It's going to be 8 and 8, 16, plus another 8 is going to be 24. 24 plus 6 is 30. So this larger one has a perimeter of 30. I wonder what the perimeter of the smaller one is. Did you see how I did that? So notice we did small to large, and then I found the perimeter of the large one, and I'm going to find the perimeter of the smaller one. And so I'll do a little bit of cross multiplication. 90 is equal to 4 times this question mark. Let's change the question mark to an X, right? Because nobody uses a question mark for a variable. Maybe we should though. Anyway, so divide both sides by 4. When I do that, X is equal to, well, 4 goes into 9 2 times with a remainder of 1. 4 goes into 10 2 times with a remainder of 2, which 2 over 4 gives me 2.5. So the perimeter of this guy is 30, while the perimeter of this one is 22.5. And they didn't give us units, so I'll just leave it at that. I hope that made sense. So we got to use this little last theorem here, and I hope that you guys feel comfortable enough to do section 7.2. I look forward to talking to you soon. Take care.